I'm Masaki Ozaki from Kyoto University. It's an honor to be here, and thank you for giving me this opportunity to talk about our recent study. So the title of this talk is Avoiding a Negative Sign Problem in Simulation of the Quantum Annealing or Quantum Monte Carlo Simulations. So I will give you a take-home message. So we have performed the quantum Monte Carlo simulation for a class of non-stochastic Hamiltonian. So for example, this is a typical example of non-stochastic Hamiltonian. So this term is transverse field. So and this term is antiferromantic XX interactions. So all-to-all connections. So we have performed this quantum driver Hamiltonian case. We have performed the quantum Monte Carlo simulation, and our method can be generalized to the class of the non-stochastic Hamiltonian in the form of these functions. So and we propose two methods, two strategies to simulate a quantum Monte Carlo simulation. One is adaptive quantum Monte Carlo simulation, and one is a data analysis approach. So this is the result. So we have performed quantum Monte Carlo simulation for the ferromagnetic interactions all-to-all connections, and with a magnetic field and transverse field and antiferromantic XX interactions. So this is non-stochastic Hamiltonian. So this is a result for the energy and longitudinal magnetization and transverse magnetization. So the red point denotes the result of the quantum Monte Carlo simulation. And the blue solid curve denotes the exact situation, because this can be exactly solved by use of the mean field analysis. So we choose this model for validation of our method. Of course, we can generalize any systems for something like the spin glass model in the z-axis. So, and we may use quantum driver antiferromantic XX interactions. And we propose two methods. So this is the second one. So this is the second result. So similarly, we obtain the consistent result with the exact situation. So of course, you are interested in my study. So I would like to review quantum annealing and its improvement by use of the non-stochastic Hamiltonian. So all of you know, so this is a standard way of the quantum annealing. So then we consider the target Hamiltonian like that. So then we add the transverse field as a quantum driver Hamiltonian. So then we trace the ground state, instantaneous ground state, by slowly tuning the strength of the transverse field. We can obtain the ground state of the target Hamiltonian. But sometimes we encounter the phase transition. So if the second order phase transition exists during the quantum annealing, so then this is characterized by the energy gap closure in the power law behavior. So then the computational time is longer and longer in the sense of the power law behavior. So and sometimes we encounter the first order phase transition. This is the obstacle. So the first order phase transition involved in the exponentially closure of the energy gap. So then the computational time will diverge exponentially. So this is a bottleneck of the quantum annealing. So, but a few challenge for avoiding the first order phase transition in the quantum annealing. So the Japanese researchers, Dr. Yuya Seki and Professor Hidetoshi Nishimori, introduced some elaborate quantum fluctuation. So in this case, they introduce antiferromagnetic XX interactions, so non-stochastic Hamiltonian. So these terms is a standard quantum annealing procedure. In addition to these terms, they introduce antiferromagnetic interaction like this. So then they have succeeded in avoiding the first order phase transition during the quantum annealing. So in some sense, for a class of the problems, so they have succeeded in the case of the p-body Ising, ferromagnetic Ising model case and Hopfield model. So Hopfield model is a class of the spin glass models. So this is a kind of the phase diagram. So the red curve denotes the phase boundary involved in the first order phase transition. So and the green curve denotes the phase boundary involved in the second order phase transition. So according to the standard way of the quantum annealing, so they trace these lines. So therefore, they encounter the first order phase transition. So, but if we introduce additional term, antiferromagnetic XX interactions, we can avoid this phase boundary involved in the first phase transitions. Of course, you know, as in the Helmut Kasgraver's talk as the first day, so antiferromagnetic XX interaction or non-stochastic Hamiltonian will be helpful for fair sampling of the ground systems. So, but however, the antiferromagnetic XX interaction or non-stochastic Hamiltonian will generate negative sign problem if we perform the quantum Monte Carlo simulation in a standard way. For instance, the transverse field terms, we decompose these terms to the ferromagnetic interactions between the different Toronto slices or Toronto replicas. So then, the antiferromagnetic interactions, if we perform the Suzuki-Toronto decomposition to this term, the result leads to the negative sign and minus of the probability. So therefore, it is difficult to perform the quantum Monte Carlo simulation, and this is difficulty to estimate the accurate estimation of the thermal expectation. So therefore, this is the motivation of this study. So can we simulate the antiferromagnetic XX interaction or a class of non-stochastic Hamiltonian in quantum Monte Carlo simulation anyhow? So this is a part of the solution. So how to simulate non-stochastic Hamiltonian? So we set our problem. So we deal with this class of the Hamiltonian. So this is a target Hamiltonian, and this is a quantum driver Hamiltonian. So f of x is any function. So but the argument is a correction of the x terms. So this is the empirical average of the x spins. So this includes a wide range of the non-stochastic Hamiltonian. So of course, including the antiferromagnetic interaction, XX interactions like this. So f of x means gamma x minus small gamma m powered to the n over n over 2. So this is a transverse field term, and this is the antiferromagnetic XX interaction terms. Of course, we can generalize these terms, 3-body XX interactions and 4-body XX interactions, etc., etc. So, but they do not include locally different interactions like the spin glass interactions. In the XX interactions, ZZ interaction is okay. So, and they do not include short-range interactions. So, for example, in this case, antiferromagnetic interactions is long-range and all-to-all interactions. So, this is a specialty of this model. So then, we show some trick point. So we use a useful technique in the mean field analysis. So in the mean field analysis, we define the order parameter of the systems. So in this case, f of mx, mx means transverse magnetization. So then we consider the constraints by use of the delta functions. So then we introduce auxiliary invariable like this. So this is a constraint of the systems. So this is the order parameter of the systems. So, and we consider the integral form of the delta functions. So then we obtain the effective model like this. So this is after performing the Suzuki-Toyota decomposition, and we obtain an effective model. So tau denotes the number of the Toyota slice numbers, and the beta denotes the inverse temperature, and this is the original target Hamiltonian. And this is a quantum driver Hamiltonian, but we decompose these terms like this. So then we find this model is effectively the same as transverse field Ising model. So but the value of the strength of the transverse field can fluctuate. So then we use the saddle point method. So the saddle point determines the strength of the transverse field. So the transverse field is determined by f prime, the derivative of the function of f. So and determined by the transverse magnetization. So therefore, this transverse field can change, can fluctuate according to the instantaneous value of the transverse magnetization. So this is a cartoon of the main idea. So this model has adaptive transverse magnetic field in some sense. So usually we consider the fixed value of the transverse field independent of the local transverse magnetization. So like this. So but in this case, if we simulate a class of the non-stochastic Hamiltonian, then the effective transverse field can change according to the value of the instantaneous transverse magnetization. So therefore, we propose the first strategy, first method to simulate a class of non-stochastic Hamiltonian like this. So we name this method adaptive quantum Monte Carlo simulations. So let us consider the usual quantum Monte Carlo simulation for the Ising variables. So the strength of the transverse field is determined by this equality. So after simulating the quantum Monte Carlo simulation for evaluating the transverse magnetization, so after that we change the values, we change the strength of the transverse field according to this equality. So therefore, we summarize this scheme. So the antiferromagnetic XX interaction or the other term of non-stochastic Hamiltonian, we consider the integral representation of the order parameters. So then we use a saddle point. So then we obtain the effective model with changing the value of the transverse field. So this is a transverse field determined by the instantaneous value of the transverse magnetization. And we perform the usual quantum Monte Carlo simulation to obtain the estimation of the transverse magnetization. So this is the result shown again. So yes, this is a close-up of the result. So this is a case of the energy. So and we plot our result depending on according to the system size, linear size spin number of spins 4, 8, 16, and 32 like this. So and we also plot exact solution with gamma equal non-zero 1. So yes, this is a case of the longitudinal magnetization. So like this. So this is the exact solution. So if we increase the number of the spins, so we obtain the asymptotically accurate result consistent with the exact solution. Also in the transverse magnetization. So we obtain the consistent result with the exact solution, and we can perform our method similar to the standard quantum Monte Carlo simulation under the transverse field. So, and we also propose another method. So this is a data analysis approach. So remember that trick point of this method. So we obtain the effective transverse field Ising model. So that this is the original target Hamiltonian, and this is a quantum driver Hamiltonian. So the M tilde is changing according to the tentative value of the transverse magnetization. So the strength of the transverse field is equal to something like that. So therefore, we perform the quantum Monte Carlo simulation by changing the value of the strength of the transverse field. So then after that, we list results of transverse field Ising model. So then we find consistent result with strength of the transverse field is equal to given by this equality. So depending on the value of the transverse magnetization. So like that. The red point denotes the result obtained by the quantum Monte Carlo simulation for the transverse field Ising model, stochastic. So then we plot some functions. So this function generated by this equality. So the strength of the transverse field is determined by the f of derivative of the function f. So in the case of the antiferromagnetic XX interactions, the f prime inverse of the functions is linear functions. So then we plot the linear functions for the given the value of the gamma and the small gamma. So then we find some cross point. So then we obtain the consistent point, consistent result. So then we replot, so we replot the cross points of the curves. So then we obtain non-trivial result for the non-stochastic Hamiltonian just from the trivial result for the Ising model with the transverse field. So this is the result scaled up the result energy and longitudinal magnetization and transverse magnetization like that. Okay, so we obtain the consistent result with the exact solution, and we can generate any result for the non-trivial value of the small gamma and the large gamma depending on the parameters. So we summarize our study. So we have succeeded in avoiding the negative sign problem for a class of the non-stochastic Hamiltonian. For example, the antiferromagnetic XX interaction. So one method is adaptive quantum Monte Carlo simulation, and the other method is a data analysis approach for the trivial Ising model with the transverse field. So and this method is not only simulation in classical computers. So of course we implement changing according to the instantaneous value of the transverse magnetization. We may implement hardware, the web and Google and MIT Lincoln or something like that. And we may test the effect of the non-stochastic Hamiltonian for the fair sampling of the ground state. And we can implement antiferromagnetic XX interaction or non-stochastic Hamiltonian to the classical computer. So therefore, we may generate fast quantum-inspired classical algorithm. So therefore, we open the way to understand a non-stochastic Hamiltonian for a class of the non-stochastic Hamiltonian. That's all. Thank you.
Hi, I don't understand why you think that the system has sign problem. Is it because of the sigma x terms? Can you go to the Hamiltonian, this one? So, okay, perfect.
Oh, yes, yes.
So what if you change your x's to z's? And your z's, it doesn't matter what is x and what is z, right? So when you change x to z and z to x.
Of course, yes. But this Hamiltonian is, of course, trivial, but just for the test of this method. We can generalize our method to the case of the spin glass asymmetric problems.
So, but you agree that this Hamiltonian has no sign problem, would you agree?
No. This Hamiltonian includes a negative sign problem in the standard way.
Yeah. What do you mean in this? I'm just saying that this Hamiltonian has no sign problem. It's very easy to efficiently simulate it. because you just change bases from x to z.
Yes, yes.
When you, when you do that, then you get on the diagonal terms, you get the antiferromagnetic. And in the off-diagonal terms, so you see the minus j will multiply the sigma x terms, which makes the matrix elements negative as you want them to be in the stochastic picture. So what I'm saying is that maybe your method has, you know, a generalization.
Yes, yes, yes. How about case p-body interactions, x-x-x interactions?
I'm sorry?
P-body x-x interactions.
It's on the contrary. If you move x to z, then you can take, you know, 12 body x.
How about the case with a spin glass Hamiltonian?
Okay, so I think if you're saying that your method works for the spin glass Hamiltonian, that you probably should have tested it on this Hamiltonian, because this one certainly, or at least looking at the Hamiltonian, maybe I'm missing something, does not exhibit the sign problem. But
maybe that is a problem of the definition of the non-stochastic Hamiltonian, because usually the non-stochastic Hamiltonian is discussed in the computational basis. If we some tricky transformation to the basis, of course we may remove the negative sign problem, but a priori we do not know how to solve, how to remove the negative sign problem in a general case. But at least in general, our method is remove the negative sign problem with sorry, just a minute, this kind of the subject. Very strong, very wide range of the applications.
I'd be very interested in seeing them. But
yes, of course, of course. Yes, yes. For this class, we may find some tricky transformation. Of course, I agree with you, yes.
So, actually, if you allow me, I have two questions. Okay. So one is about, can you go on your definition of M tilde x?
Sorry, again, please.
Can you go on the definition of M tilde x?
N theta?
M tilde x?
Yes, 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 yes. Okay, sorry. This one? Yeah.
So it's the Lagrange multiplier from the delta function, right? So, and you're saying that you get M tilde from saddle point.
Yes.
But is saddle point, I mean, saddle point is good when, you know, the thing in the exponent is large. But if tau is the number of Trotter slices, that's large, right?
Yes, yes.
And in the exponent, you have something small.
Tau beta over tau is small, yes, but the prefactor exists as a system size, n over n, yes.
So this works if your system size is larger than...
Yes, 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 yes.
Okay, so because I think effectively it's working because f is quadratic. It's a quadratic function. So I mean, there are, no?
Of course, but we generalize this function form.
And you still think that the saddle point will be a good approximation?
Yes, just approximation, because in a sense of the exact sense, we have to perform the Langevin dynamics for sampling the continuous value of mx and m tilde x.
Yes.
But we consider the system size infinite limit, so then we take the saddle point. Yes.
So, and the other thing is about the efficiency of this thing, because I saw that the largest system sizes you consider is 32.
Again, please, sorry.
The largest system sizes that you considered is 32.
32?
Yes, in your, just go, the largest n is 32.
Ah, 32, yes. Yes, okay. This is a
That's not big.
But so, fairly good result.
I mean, you can do hexadiagonalization if you want at that size, right?
But
so, what's the efficiency of your method? Do you think you can go to larger system sizes?
Yes, of course, but usually we hope we take some asymptotic limit of the system size large limit. So therefore, this is just, of course, this is just a finite size simulation, but we hope and we get the asymptotic result by extrapolating of the
But
results.
you know, because this is a simple problem, on other problems you might not be able to see the asymptote unless you go to n equal 200 or something.
So maybe one last question? Anyone? No? Okay, then with that, let's thank our last speaker.
Thank you.